now we are going to prove some obvious things. When you come up with an abstract definition of something, one thing that you might be worried about is like, did I list enough conditions? Like we said, oh, if it satisfies 8 conditions, then we will call that a vector space, right? But was that enough? Maybe we had to come up with 9 or even 10 different qualifications for something to be a vector space. And what I'm listing here should be like so obvious. Like there should be, so in other words, this 1.25 in our textbook in linear algebra done right has this statement. There is only one additive identity. And it seems so obvious, right? I mean, if you think about Rn, the only additive identity is what? It's the one 0, 0, 0 everywhere, right? So from that experience, you know that this should be true. But then the question is like, should I list that as property 9, or does that follow from the other properties that I listed? See, you don't want to come up with 27 qualifications for being a vector space, because then you have to do so much work to show that something is a vector space, right? You want to keep the list minimal, but with the understanding that some of the other properties you don't have to list them, because if you have these 8, you can deduce them. Right? So that's why you end up having to show these seemingly obvious things, but it's not obvious. What the real mission of this, so I think nowadays people say, did you understand the assignment, right? Yeah. So the assignment here is to be able to prove this using only the 8 properties of being a vector space, okay? So that once you accept the 8, everything else follows, right? Okay, so let's see. And for these, the obvious thing, when you try to show that something's unique, the obvious thing is like, what if it's not? Yeah, and then try to show that in the end they end up being the same. Okay, so proof. Suppose W1 and W2 are both additive inverses. Okay. And so to go back to my comment about solving mazes, you have to start from the beginning and end. What should be the end statement?
They're equal.
W1 should be equal to W2, right? So we have to start from this, and this is where it should be ending. Now, that means to prove that these two are equal, we better start from W1 and end with W2. And it's like equal, 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 and you have to end at W2. Make sense, right? Okay, so how do you do that? Well, you try to list the properties that you know about 0. So these are secretly really 0 elements, right? So what does the 0 element satisfy? You take any vector, u plus w1 should be? U. And w1 plus u should be? U as well. And this should be true even if you have 2 as well, right? Okay, so what we can do is we can now do the following. W1 is equal to W1 plus W2. Why? Why is this true? Because, what assumption am I making?
W2 is the additive inverse.
W2 is an identity, so W1 plus any vector plus the identity element, which is secretly 0, W1 plus 0 should be W1, right? Okay, so W2 is an identity. Okay? But then, this time view this as the identity. Then what do you get? If this is the identity plus anything is that thing, right? So this time, because W1 is an identity. Okay, what now? What now?
They're equal, right?
So we're done, right?
Yeah.
W1 is the same as W2, so we're done. Right? That's the proof. Okay, we show that if you have two identities, then they have to be equal. Done. Alright, so let's try to just to show this next one. This next one is saying that the additive inverse is also unique. How do we prove that? Well, proof. Suppose V and W are additive inverse of U. Now for this, what are we trying to prove? We have to show uniqueness, so what should we prove?
V and W are equal.
V and W are equal, right? Okay. Now, this is proof-heavy course, okay? Until last lecture, I was showing you all kinds of calculations just to make sure that you remember what was done in the previous linear algebra course. But this version of linear algebra is proof-heavy course. You have to learn how to prove things. I'll be assigning you more proof problems, okay? How do you prove things? Well, proof is not a linear thing. Like, calculation is linear. You have algorithms. You just follow the algorithms, and there you have the answer, okay? The reason so many people struggle through this class is because suddenly they have to do something that's non-linear. You have to go back and forth. It's exactly solving a maze. You have to start from the beginning, start to the end, and then look at these parts that it's really confusing. You have to sort things out, and only after sorting out everything, you kind of discover the proof and you write down the simplified version. And that kind of approach can never be learned just from the textbook, because textbooks hide that nonlinear part and they only show you this organized proof. And you feel like, where did this proof come from? Yeah. You have to overcome that, okay? So I'm going to be writing a lot of things that doesn't get included in the final proof. You don't have to write them in the notes. Maybe it's better not to write them, just so that when you can reread it later, it makes more sense. But that's why I'm recording this lecture. Try to review the lecture and see the nonlinear part and how that gets organized in the final proof. Okay? So we have V and W. We have to make it equal. And then just list what can be said. We know that V and W are additive inverses of U. What does that mean? U plus V is 0, right? And then U plus W is 0, right? That's what we have. Is there any way we can start from V and end up with W? Well, what about this? Maybe I can say V is equal to V plus 0, right? And then rewrite 0 as this guy. Yeah. Because that way, I'm trying to get to W. How do I get to W? I have to involve W somehow, right? So I can do this and then say, okay, what if I put u plus w like that? Is there any way I can get rid of the v and u and end up with w? Do you see it?
E plus U equals W, or equals 0.
Yeah, these two will add up to 0, and then when they cancel out to 0, you end up with w, so you're done. That's how you're going to prove it, right? So now that we have a plan, we're going to erase everything and write a cleaned up proof, which gets written in the textbook, which is really bad for you if you're only trying to follow that, okay? That's why so many people end up trying to memorize all the proofs and the solutions to the exercises and they hope that one of these just appear verbatim on the exams, and they barely pass that way. But that's like doing it the hard way. It's much easier to think through the proof. Once you learn this technique, then this class actually becomes the easiest class. It really is, yeah. That's how you should. You have to change the perspective of how you approach things, right? So we're going to start from v. We say v plus 0. V is v plus 0, and this is additive identity. Or to put more words, 0 is an additive identity. That's why this is true, right? This equals sign. Then we can say v plus u plus w. And why is 0 same as u plus w? That's because w is the additive is an additive inverse of u, right? And then we want to cancel these two, but to cancel those two, we better group them together, right? What property is this?
Associative.
Associative property, right? Okay, and then v plus u is 0. And why is this same as that? Because v is an additive inverse of u. Just like divide your logic that we just thought about into detailed steps and think about how to justify every equal sign. You keep doing that and then you'll get used to this, all right? And then 0 plus w is w because 0 is additive identity. This is not the first time you had to do this for most of you. Most of you took high school geometry, right? How many of you took high school geometry? Yeah, over there you had to list every step and put reasons, right? It was a 2-column proof. It's almost like that, okay? Yeah. All right. Let me write another. But after this, we're going to put another definition. Since the additive inverse of u is unique, we will denote by negative u for v. This is actually the important word because we prove that it's unique. We can say the. Before in the proof we had to say a because we don't know if it's unique, but now it's unique. We can say the additive inverse of u. Okay, and comma, and write u minus v for u to mean u plus negative v. So now we have defined what a subtraction is. Because the additive inverse is unique, we can define a subtraction, which is subtracting two vectors means you add the inverse of the second vector. Okay? All right? Show these. Again, I'll start with the blue marker that I'm going to erase. Let's think about what this is. All right, so you have 0v equals to 0. I have to show that how I'm going to do that. Both of these has something to do with the distributed property because see, we're really saying so 0 plus 0 has the property that 0 plus 0 is 0, right? So so if we have 0 plus 0 times v equals to 0v, and then apply the distributed property, then you're going to end up with 0 plus 0v plus 0v equal to 0v. And then once you have this, then you can subtract 0v both sides, and that's going to end up giving you 0v equals to 0. So that's the idea. It has to do with the distributed property. But what makes me a bit uncomfortable is that we can subtract 0v both sides. Can you do that? We were doing that for regular real numbers and complex numbers, but are we allowed to do that for vectors? Is that true? Well, we could argue that it's true by so what am I trying to say? If I have two vectors u and v, then you can subtract two things and they should still be the same. Well, how would you prove this? Well, see, if u and v are the same, then u minus w is, since u is same as v, it's a principle of substitution. If two things are equal, you can replace one by the other. So you can replace u by v and say this is v minus w because I've replaced the same thing by another. But then look what happened. This is the same thing as saying I'm subtracting w both sides. Is that okay? Yeah. So that's why such an argument does work. However, a lot of writers of textbook would try to avoid that altogether because they don't want to have to explain this again, and makes that kind of thing makes the proof a little more complicated. So they want to write a cleaned up proof, and on the way that makes the proof more inaccessible. Yeah. Oh, well, let's try to do a different approach here. So I want to say, I want to show this, right? So I should begin by 0v, and then I have to end up with 0v, right? 0. That's what I want. 'Okay, well, we'll just divide it into two parts. We'll just use this one first, and then, actually, use this one first, right? And then, yeah, okay. So let me, so we'll start with this. 0 plus 0v is 0v since 0 plus 0 is 0 in F, okay, in the base field. But then this left side you can multiply this out so that 0v plus 0v is 0v. And this is because of the distributed property. Okay, so with this at hand, what I'm going to do is I'm going to say 0v is equal to 0v plus 0 equals to 0v plus 0v minus 0v. Okay, all right, so first, why is this true? Because 0 is the additive identity, right? Okay, what about from here to there? Well, this one is what we proved, right? This is the way we write down the sum of any vector with its inverse, right? So anything added to its additive inverse is the same as 0, so this is simply the additive inverse. But now we can combine these two. And what is that? Going from here to there. So we combine these two, right? That's associativity. Associativity. But now we use this that we just proved. Okay. So from above. Okay, and then anything added with its inverse should be 0. Any vector minus itself is 0. This is additive inverse. Which is actually the same thing we used here as well. Okay? So at the end we started from 0v and ended with 0, so the proof is done. So that's one thing. I'm pretty sure the book has the proof slightly different. So please read the book, see what it does. There are many. So here I try to avoid having to add two things both sides, but I just checked the textbook and it doesn't do it this way. Rather, it just starts from here and then says you add minus 0v both sides, and they cancel and they cancel. So it doesn't even talk about associativity or anything. Cancel, cancel, and you get 0v equal to 0, which is what you want to prove. So another thing to keep in mind is that when you are asked to prove something, there's like different levels of detail that you have to go through. And the textbook authors, they have to make a decision. Do you need to prove everything to the detail like this, listing every property? Well, for some things, maybe yes, but once you accept things, then you can simplify the proof as you go. Okay, so I wrote a proof that's like very detailed, justifying every step, but one in the textbook is a lot simpler, right? Okay, so let's do that here then. We have that a times 0 plus 0 is a times 0, right? Where 0 is the vector because 0 is a additive identity, 0 plus 0 is 0. And then if you apply the distributed property, you get a times 0 plus a times 0 equals to a times 0. And now you subtract a times 0 both sides, and you get a times 0 equal to 0. Okay, so that's the simplified proof. And we'll just, at this point, we're going to say all these associativity and all the other ones are obvious, so we'll just write it like that, okay? Okay, so how do we show that negative 1v is equal to negative v? Well, you just have to show that negative 1v acts like an additive inverse, because we show that additive inverse is unique if this does satisfy the, this is the equation that says u is the additive inverse of v, right? And if this satisfies this equation for this u, then this has to equal to that, because we earlier on we showed that additive inverse is unique. Okay, so there, that's what we're going to show. Oh, I should have written this down in blue. Sorry. Yeah. So this was not my intention. Okay. So now the actual proof is I want to show that this is 0. Okay. Now this is equal to 1 times v plus negative 1 times v. What's this property? It's that one, the identity acts as a identity of the scalar field acts by not changing anything, right? 1 times v is v. This was one of the axioms, which we don't have to say. It's one of the axioms. Okay, and then we can factor the v out. Right? That was our distributed property. Well, distributed property is usually, it goes this way, this is equal to that, but in math, if A is equal to B, then B is equal to A as well. So this is like going backwards direction for the distributed property. And because this is inside a field, what's 1 plus negative 1 in R or C? 1 plus negative 1 is? 0. And then didn't we just prove that 0 times v is 0? So we show that 0. And we are done. This shows that thus negative 1v is the additive inverse of v. But I'm using the because there's only one, yeah, which is negative v. Yeah. Okay, there's only one additive inverse, so they must be the same. Okay. It's a bit complicated, but maybe it's right. I can't decide. All right, so let me show you how this could be solved. So proof number 1. Well, just write down what it means to be negative of negative v. Negative of negative v, by definition, is the inverse of negative v, right? Isn't that right? Negative v plus negative negative v is 0. Okay? But then, negative v plus v is also 0 because addition is commutative and we can, I mean, this, we know that negative v is the additive inverse of this, right? This is 0. So maybe I should write here, since negative negative v is additive inverse of negative v, okay? And this one, because negative v is additive inverse of v. Write that down, and then, but then if you look at this, you see that this is saying that, this thing here is saying, this is saying that v is negative, or v is an additive inverse of negative v, right? Because You have something plus another thing to give you 0, so this must be the additive inverse of this. But now we use the uniqueness of additive inverse, since additive inverse is unique, therefore we see that negative v, v has to equal to negative of negative v. Okay? So that's one proof by using the uniqueness, but a second easier proof is making use of this one. Okay? So let me show you the second proof. Well, since negative 1v is equal to, or vice versa, negative v is equal to negative 1v, we can say negative of negative v equals to negative 1 times negative 1 times v. But we had the compatibility condition, which is that if you have a times bv, that's same as ab times v, right? That's the compatibility condition, which is equal to 1, and 1 times v is v. That's another thing that's in the axiom, right? So that's it. We've proved it. Okay? So the second one is a lot easier.